Bismillahirrahmanirrahim. In the name of Allah, who is the most merciful and beneficent. My name is Hina Shanz, the Department B is Biotechnology, roll number 004. And the topic of my presentation is integrated rate laws for zero order and first order reaction. So, while studying these, the questions that pop up in our mind are we often want to find how the concentration of a reactant or product varies with time. For example, how long will it take for a product pollutant to decay? How much of the alternative fuel methanol can be produced in an hour from alcohol in an industrial process? How much of the sample of penicillin will be left after 6 months? This question can be answered by using formulas derived from the experimental rate law for the reactions. Now, integrated rate law. An integrated rate law gives the concentration of reactants or products at any time after the start of the reaction. Finding the integrated rate law from a rate law is very much like calculating the distance that a car will have traveled from the speed at each moment of the journey. The integrated rate law for a zero order reaction. The integrated rate law for a zero order reaction is easy to find because the concentration because the rate is constant at K. The difference in concentration of a reactant from its initial value is proportional to the time for which the reaction is in progress, and we can write as initial concentration of A minus molar concentration of A is equals to K into T. T stands for time. Now moving on towards its graph, which is as shown in figure. A plot of concentration against time is a straight line of slope minus K. The reaction comes to an end when T is equals to initial concentration of A by K, because then all the reactants has been consumed. Then first order integrated rate laws. Our aim is to find an expression for the concentration of an reactant A at a time given that the initial molar concentration of A is given in this form, molar concentration of A naught, and that the reaction has been found to be first order in A. Now to find the concentration of reactant A in a first order reaction at any time after it has begun, we begin by writing the rate law for the consumption of A. The rate of consumption of A is equals to minus D into molar concentration of A by dt is equals to K into molar concentration of A. Because an instantaneous rate is a derivative of concentration with respect to time, the techniques of integral calculus can be used to find the change in molar concentration of A as a function of time. First, we divide both sides by molar concentration of A and multiply through by minus dt. The expression we will get will be D into molar concentration of A by molar concentration of A is equals to minus K dt. Next, we will integrate both sides, and we will apply the integration here. Then we will get this expression. Then to evaluate the integral on the both sides, we use this standard form which is written as follow. And then after it we will get the final expression here, ln into molar concentration of A with respect to time by initial concentration of A is equals to minus kt. When we obtain anti-logarithm of both sides, we obtain the final expression here, that will be molar concentration of A with respect to time is equals to initial concentration of A into E raised to power minus kt. And as y is equals to ln into x and e raised to power y is equals to x. Then the two equations that we have derived are two forms of the integrated rate law for our first order reaction. As equation 1 is ln A molar concentration of A with respect to time by initial concentration of A is equals to minus kt, and the second equation is A molar concentration of A with respect to time is equals to initial concentration of A into E raised to power minus kt. The variation of concentration with time predicted by equation B, as shown in this slide in equation B, is shown in figure. This behavior is called exponential decay because the concentration of A depends on an exponential function of time. Initially the concentration changes rapidly, but it changes more slowly as time goes on and the reactant is used up. So here we can see the K small and K large slopes. We can see here the time it's the graph between time and molar concentration of reactant A. Then an important application of an integrated rate law is to confirm that a reaction is in first order and to measure its rate constant, as the equation is given as. Then this equation has the form of an equation from a straight line. ln molar concentration of A with respect to T is equals to ln initial concentration of A minus kt, and therefore a straight line with slope minus k and will be appear here. Then some rate laws depend on the concentration of more than one species. For instance, oxidation of iodide ions by persulfate ions follows the rate law. The rate of consumption of iodide ions is mentioned here. In such cases, the analysis can be simplified by ensuring that one species remains effectively at the same concentration throughout the reaction, and so we can be treated as a constant. One way to do this is to start with persulfate ions in such a high concentration that their concentration barely changes in the course of the reaction. For instance, the concentration of persulfate ions must be 100 times as greater as the concentration of iodide ions. It's same like the limiting reactant. So even when all the iodide ions have been oxidized, the persulfate concentration is almost the same as it was at the beginning of the reaction. Because persulfate ion is virtually because this S2O8 raised to power minus 2 is virtually constant, the rate law can be written as rate of consumption of iodide ion is equals to K dash into molar concentration of iodide ions, where K dash is equals to K into um, S2O8 raised to power minus 2, another constant. We have turned the actual second order reaction into a pseudo first order reaction, a reaction that is effectively first order. In a first order reaction, the concentration of a reactant decays exponentially with time. To verify that the reaction is first order, plot the natural logarithm of its concentration as a function of time and expect a straight line. The slope of a straight line is minus k. So that's it. It was my presentation. I hope that you like it, and thanks once again.